So, good afternoon, my dear students. Today we will discuss the relative velocity method. Okay. So there are two methods to find out the velocity in a particular mechanism. One is instantaneous center method, another is relative velocity method. So instantaneous center method we have discussed in the previous lecture. Today we will discuss relative velocity method. So all of you know this. What is relative velocity? So relative velocity, that means velocity of a point with respect to the another point. So in that particular mechanism, the relative velocity is velocity of one link with respect to the another link, or maybe point on a particular link with respect to the another point of that another link. Okay, so there are two types of velocity. One is angular velocity, another is linear velocity. Okay, so if you consider a point, a velocity va, another point suppose b, vb, so that velocity is known as absolute velocity. Now if you find out the relative velocity, then that relative velocity will be VBA, that means velocity of B with respect to A, or you can find out velocity of A with respect to B. Okay, so we can find out, in that way we can find out the relative velocity. VBA, that means VB minus VA, or VAB, that is VA minus VB. That is the relative velocity. So that velocity, relative velocity method we will discuss here. Now, if you consider a link, and one end of this link is fixed, suppose that is O, that is A. Okay, so suppose this link is rotating with some angular velocity omega, OA, with some angular velocity it is rotating. Actually, all types of motion are we have considered in instantaneous method, that is pure rotation with respect to some imaginary point. So it is rotating with some angular velocity. Now, what will be the direction of this velocity? Suppose velocity VA. So VA is equal to, you know, V is equal to R into omega. Omega, that means omega OA. V is equal to R omega. Now, what will be the direction of this velocity? What will be the direction of this velocity? So velocity, we can write V AO, that means velocity of point A with respect to O, because O is fixed here. As it is fixed, so VAO, because velocity will be 0 here. Okay, so velocity will be VAO. So what will be the direction of this velocity? As it is, suppose it is rotating in a clockwise direction. So direction of this velocity will be perpendicular to the line VA. That will be perpendicular to the link OA. So as it is clockwise, so direction is this side. If it is anti-clockwise, then direction will be perpendicular to this line OA. Okay. Now, if you consider another link here, A, O. Now, that is angular velocity omega, this rotating. Now we know omega is equal to theta by t. So angular deformation or angle turn with some time, suppose at a particular time its angle turn, okay, Now, if you consider different points here, suppose A, B, C, D, E, F, G. So you consider different points. So that angular velocity omega, that will not change, and that omega will remain same if you consider all points in the particular link. Omega will never change. Okay. So this angular velocity remains same throughout the link, but this linear velocity, suppose this point is here, this point is here, this point is here, this point is here, this point is here. You can see this linear velocity is changing because v is equal to r into omega. Okay, so r is changing, that means omega v will be changing. That means in case of linear velocity, in a particular link, linear velocity will change with respect to the length of the link or radius of the link. Okay. Now, here we are considering that link which one side is fixed and other side is free. Now, if you consider in that cases, what will be the relative velocity? That relative velocity, that will be VA. That means your R is there, or AO into omega AO. That is the relative velocity. Okay, as one end is fixed. Now, if you consider a rigid link, that means there will be no deformation due to the application of this load. There will be no angular deformation, no linear deformation, no deformation will be there. So in that case, A, B. So that is a rigid link. So we need to find out the relative velocity of B with respect to A, or relative velocity A with respect to B. Good. So in that cases, suppose velocity VV, direction of this point B is VV, and here VA. So this direction of VB and direction of VA, it has two components. One is along the link. So we take that component, that is VA. So if you consider this makes an angle alpha and that angle is beta, so we can say that is VB cos alpha and VA cos alpha. Now, whether there will be any relative velocity along the plane, whether there will be relative velocity of B with respect to A, whether there will be any relative velocity, there will be no relative velocity between A and B. In that case, VB is equal to VA, because if there will be some relative velocity between A and B, as this link is fixed, that means solid link, no deformation. So if the relative velocity will be there, in that case it will try to elongate or it will try to shorten. So as it is rigid, so there will be no relative velocity between B to A. Okay. So in that cases, VA is equal to VB. Now if you take another component, so VB sine alpha, VA sine alpha. So we consider another component. Now, what will be the relative velocity of B with respect to A? Suppose VB A. So VB minus VA. Okay. So what will be VB minus VA? VB is VB sine alpha. If you consider one side is positive, another direction is negative, so that will be VA minus VA sine beta. So that will be VB sine alpha plus VB sine beta. So in that case there will be some relative velocity. Okay. So due to the relative velocity there may be some rotation clockwise or anti-clockwise, there will be some rotation. Okay. So similarly we can find out the relative velocity A with respect to B, VA minus VB. So in that case there will be some relative velocity. Now using this relative velocity we will try to solve. We will use this in a 4-bar mechanism and we will find out the relative velocity or velocity of a point in a particular link with respect to another point. Okay. Now you consider 4-bar mechanism. So there is a 4-bar mechanism. So there is link number 1, 2, 3 and 4. So that is crank. So it is rotating with some angular velocity. Suppose that is O, A, B, C. Okay. So V, AO is there. Suppose it is known with some angular velocity. Because if this length is known, so we can find out this velocity. Because omega is known, so we can find out the VA. Okay, we can find out the VA, that is known. Now, or maybe some angle is given. Now we find out the velocity with relative velocity method. Okay. Now, as this is a crank, that crank is rotating. This crank is rotating. That will reciprocate, and that will also suppose rotate. Okay. Now, if you draw the velocity diagram, that diagram is called configuration diagram. So from configuration diagram to, if you draw the velocity diagram, in that cases this capital letter, it will be converted into small letter. So small letter indicates velocity. Now suppose here this is the method. So by this method you have to take O and C as a reference point. The fixed point you have to take reference point. Suppose that is A and C. That is the reference point. Now from the reference point, so before going to find out the velocity diagram, you have to take some suitable scale of this velocity, because this is known velocity. So you have to take some suitable scale. You have to take some suitable scale. So from A to C, A, as it is fixed, so what will be the velocity VA? It has some values. So take these values, because it is perpendicular to link OA. So you take the same line, which will be parallel to this line. So you draw it. So that is OC, sorry, that is OC. So this length is known. So direction that is VA. We can write VA. Okay. Now you can see here velocity of B with respect to A. Now we are considering this link AB. Now this link will reciprocate or oscillate. This is oscillate. Okay. So what will be the direction? Direction will be perpendicular to the link. Perpendicular to the link. So we draw another line parallel to this line. But here we do not know the dimension or the length of the link. We do not know the length of the. We do not know the velocity. Okay, we do not know the velocity VV. Velocity B with respect to A. So you can consider VV. That velocity is unknown. So their velocity will be anywhere between this line. So that will be anywhere between this line. Now where it will be this line, we do not know. Now between B and C, velocity of B with respect to C. Now as it is also rotating, so direction will be perpendicular. So the direction will be perpendicular. Now you can see, if you consider C, so from C you take a line which is parallel. So this line, it will intersect this line. So that intersecting point is B. That intersecting point is B. Okay. Now this is VA. So velocity of B with respect to A, that is VBA or VB. Simply can say VB. And velocity of B with respect to C, that is velocity of B with respect to C, or you can say velocity of B with respect to A. This velocity of B with respect to C, that is BBC. Okay. So we can find out the relative velocity by using this velocity diagram. Now you measure, because earlier we have taken some suitable scale. Now you convert this scale into original value. So we can have this length of this. Okay. So by using this method, we can find out the velocity in a particular point. Suppose if you need to find out the velocity here, suppose at point E. At point E, you need to find out the velocity, or that is A, VA. So A to B. Suppose you need to find out the velocity here at the midpoint. So that will be the velocity, because the length is known. Length of this link is known. Line is known. So we can find out the velocity. So that will be VE. Okay. So in that way you can find out the relative velocity. You can find out the velocity in any point of this link. Any point of this link we can find out the velocity by using this relative velocity method. Now if you consider this is case number 1. Now if you consider another case, suppose O, A, B, C. So these two links are parallel. Okay, these two links are parallel. So that is rotating with some angular velocity omega. Okay. So length of the link is known. Now we will draw the velocity diagram. Now for velocity diagram, again we consider the same method. So as it is rotating clockwise direction, so direction of this velocity will be straight. Now as O and C here fixed, so we take a reference point O, C. So from O and C, that is VAO, so it has some value. V is equal to R omega, omega known, this length is known, so it has some value. So you take some suitable scale. So we have got some length, some values. Now direction is perpendicular to this line, so it is horizontal. So some value will be there. So that is A. Now relative velocity of B with respect to A. Relative velocity of B with respect to A. Now that B, that will oscillate. So it will oscillate. So what will be the direction? Direction will be perpendicular. Direction will be perpendicular. Okay. So direction will be perpendicular. So if you draw the perpendicular line, because this dimension is not known, so draw a line perpendicular to this point A. Now B will be anywhere in between this line. It may be here or it may be here. It is not known. Now velocity of B with respect to C. Now it will also oscillate. It will rotate. It will rotate. So what is the direction? Direction is perpendicular to this line. So from C, you draw a line. From C, draw a line which will intersect. So from C, you draw another line. So it is intersecting this line here. That means the point B lies in that particular point. B is lying on that particular point. So from that diagram, we may conclude one thing. That if in a particular mechanism, in a forward mechanism, if these two links are parallel to each other, and perpendicular to the horizontal, in that case it will be straight. Okay. So in that case it will be straight line. Now again another thing we can conclude here, that velocity of B